thank you, Giovanni. It's wonderful to be here once again to share with you some of the physics that we discuss here, and then we're turning a little bit more to basic science from Spice Center. I remember the story between the Spice name that we just heard about on my Spice Center itself. And today I wanted to tell you some physics on Antiferromagnetic particularly the direct observation of this parity violation in the electronic structure. Oh, sorry, I think I ran away quickly. Okay, sorry, let me go back to the, okay. And particularly this is work done led by Olena Feshenko and Libor Smechial in the lab of Jairo Elmers, and of course with me theoretically Libor in my group. Let me maybe turn on the laser here. It's a little tricky to get to it. Okay, how do you turn on the laser? Okay. Oh, I see. Got it. Okay. You see the laser? Yeah, I think the laser is there. Yeah. When talking about Magnetospintronics, of course, what we're aiming is to attain and begin to make more active use of the advantage of antiferromagnets. It has similar advantage to ferromagnets that are non-volatile and radiation hard, but they have the advantage of having a non-net magnetic moment, that there's some multiple stable neuron-like states that can actually be utilized for non-conventional computing, the inherent dynamics, and the fact that there's many more materials that are antiferromagnetic. So the goal of this now decade-old new Antiferromagnetic field is the direct manipulation by electronic means and thermal means of the antiferromagnetic order, as well as make them active elements in devices and bridge the gaps in the terahertz and optical regimes. Now, so you can maybe repeat some reviews on the topic, but just to remind that to be in the same setting, ferromagnetism usually gives us this notion that there are very practical aspect to them, that there's electronically active and magnetically active materials with spin splittings that have been utilized now. It started, of course, from the discovery of GMR of Albert, and became practical in many, many ways. Antiferromagnets, on the other hand, for a long, long time, they were thought to be not so useful because they were anti in many aspects. They had the aspects that not only they didn't have any spin splitting, but they have primarily, by the Kramer's theorem, spin degeneracy. And that was governed by this PT symmetry that is involved if you just look at the spin degree of freedom ordering in this case in the typical example that Neil showed us on the bipartite lattice. And this itself often came with the fact that because of this local aspect of exchange, most of the antiferromagnets tended to be insulating. Now, it turns out that there's not only these two types. You think that that's the only things that you do have. But if you look at the band structure itself, now there's a new type of thing, which is I'm not going to talk about today, but I wanted to mention it for the people that are not so familiar with the field of the latest developments of discovering a new type of magnetic phase. We're calling this, that is a new, really basic phase based on symmetries, grounds, and the properties that it shows, particularly this outer magnetism. These are non-compensated zero magnetization spin systems, but in this case the symmetry of the system is governed by the non-relativistic physics and show a spin splitting that is now related by this rotational symmetries in the system that have a lot of the aspects of ferromagnetism, showing spin splitting that are huge, very, very large, dominated by the electric crystal field, and that can give rise to GMR effects as well, and TMR effects which not believed to be the case in for example, in this run-of-the-mill PT antiferromagnets that are spin degenerate. Here, I'm not going to talk about this, but if you're interested, there was discussed in the workshop that was organized by Giovanni in September, and also a recent talk in the YouTube channel of SPICE given by Thomas Youngworth, if you're interested on listening on those particular physics. But today, we're really focused much more on the physics of these PT antiferromagnets, which are still very interesting because once one manages to make them metallic, and this was the idea that now, that's almost since 2014, when we predicted the appearance of the Nail spin-orbit torque that I'll mention in a minute, and also a new type of switching based on higher currents that break the antiferromagnet in multiple nanodomains that were functional in terms of memory devices based on artificial intelligence and hardware. Now, focusing now on this type of physics that we can actually attain in this spin degenerate antiferromagnets, one actually attains by borrowing from the idea of in this case, the inverse spin-galvanic effect, not so much the spin Hall effect, but the inverse spin-galvanic effect that tells us that if you have inversion symmetry, you can have with spin-orbit coupling a spin non-equilibrium polarization perpendicular to the current. Taking that to the antiferromagnetic environment, you end up with the fact that if you have now two an antiferromagnetic order centrosymmetric system with two sublattices that have opposite inversion symmetry, in this case showing you the purple and the red that you see in the images, they will have locally within the unit cell this equilibrium hidden polarization or spin texture that now when you actually run a current through the system, in this case in the plane, will induce this non-equilibrium spin accumulation that couples directly to the Nail order parameter and can, at least if you have a system without a strong anisotropy, overcome it because it's proportional to the current and be able to switch it. This was demonstrated in this beautiful experiment by Peter Badley that did experiments at low currents and then showing them at the same time as XMLD experiments, so showing the correlation between these large domains that were at the center and the switching, and also observed later on by the team here in Mainz in manganese to gold. And here now coming to regime where you have also some thermal effects where most other switching, other changes in the resistance are coming along with these other systems. The new generation of manganese to gold that have now fairly low and much more control and isotropy do so a much more control switching that is not so thermally connected, but connected to the Nail spin-orbit torque. Now, this has given us lots of new ideas and physics in these systems, in this seemingly still anti-ferromagnets, meaning that they have this spin degeneracy involved in them, showing how topological, this is something that I talked about before, and that how you can manipulate the topology of the quasi-particles by switching and manipulating the Nail order parameters. That's also some in insulators, of course, some long-distance spin diffusion aspects. And in this case, what I want to tell you about is the idea of directly observing this parity violation in the band structure, which is in fact, maybe people don't think about this, but it's actually very, very rare. So this means that going back to the idea of band structure parity, in almost all the textbooks, all the ARPAS data that you actually see, you do have this parity that the energy at the K is equal to the energy to minus K. This is because you have symmetry that protects this. You have parity that will indicate that you have this evenness in the band structure. If you have time symmetry, you also will have it. If you have time symmetry with translation, you will have it. And you have time symmetry with the spin rotation without spin-orbit coupling, you also have that type of symmetry, and it covers a lot of physics and a lot of the systems. If you have parity broken even, but the time is still the parity symmetry of your system, you do have an evenness, not in the spin sector, but if you are in unspin resolved ARPAs, you would also have that, as we know from the Rashba systems, for example. The only way to, of course, break this parity if you break everything. If you break band structure, both in the interfaces, everything is broken, you will, of course, break this symmetry. But what was not expected and is not known is that the Kramer's degenerate system, that you don't break that Kramer's degeneracy, which happens for these PT antiferromagnets, you would see that. And this was the prediction that we did, that Lewis Mejia did on this particularly manganese to gold, where you can see in this case the manganese to gold in this structure where here the nail order is on the X direction. Then if in this case without spin-orbit coupling, which I show here in this diagram on the left, you do have that evenness, as I mentioned. E of k is equal to E of minus k, because you have these two mirror planes, in this case the mxy, mx bar y plane, asymmetries of your system. In this case, in the spin group theory base that decouples spin and the orbital degrees of freedom. Once you put spin-orbit coupling, which in this case in manganese to gold is quite strong, you end up with, of course, in a magnetic symmetry group, which is different. And in this particular case, it breaks this mirror symmetry of mx bar y, as you can see here. And in this case, the connection between this band structure and that band structure with opposite nail order, or opposite time scales in this case, is essentially a coupling this mirror symmetry with time inversion, which is the only one to couple the systems. So this, in this case, breaks that directly. Now, to observe this, we are going to use photoelectroemission spectroscopy, PEEM, which one knows directly. Quite a few know this. This is just by doing essentially a probe excitation of photoelectrons, pump probe experiments, where now the photoelectrons are the optically active things, similar to optical imaging, where now the focal points on the real focus and planes can be used to measure, in this case, the real images or the momentum image parallel to the plane of the sample. Now, the thing that really made this possible, these experiments possible, is the new development that was done here in Mainz, a new machine called time of flight momentum and microscopy of these photoemission experiments that allows for the energy now to be measured in terms of the time of flight of the free electrons from the sample. And that allows for a much rapid superpolarization of the spectra, the ARPES spectra that one can obtain from the optical systems. Instead of having to measure the energy by means of electron deflection by magnetic field, as is usually done in many of the prior versions of ARPES. As I said, to go between the time of flight and momentum spectroscopy just simply changes the focal plane, similar to what is standardly done. And here one can essentially get from the same apparatus, go from the momentum image to the real space image as a function of energy, of the binding energy of the photoelectrons. And the spin part of the resolvent, you can actually do this by just a typical polarization perpendicular or parallel to the plane of the reflection from the sample. And this is X-ray photoelectron momentum spectroscopy, which is also standard in most of the ARPAS studies. For details of the experiment, being the fact that I'm not an experimenter, I'm a theorist, I recommend this review of by George Schoenesen and Jairo Elmers on this time of flight photoelectron momentum microscopy with spin filtering that is described in this preprint, a recent preprint of their apparatus. This is an apparatus, by the way. It is actually now quite popular and has been actually been implemented in most of the major user facilities that we have in Europe, and also being installed in the US. So back to the experiment. Now let's discuss the experiment that was done in manganese to gold to observe this parity violation. The first one is to using the PEEM mode in the real space microscopy. You have the sample here shown in the fairly large, about 20 or 30 microns diameter, 50 microns diameter circle. And we measured here the photoemission, the magnetic linear dichroism images which can distinguish now. We choose to do them because it's as a function of energy. They're sensitive as a function of energy around 0.6 electron volts binding energy, because that's where it's the most sensitive. And here, as you know, this can distinguish now between the nailed direct orientation of the nail vector. So here you're seeing domains of the nail vector orientation. And I mean orientation, meaning that you don't know if the nail vector is pointing to the right or the left. You just know that it's lying on a particular axis. The blue in this case indicates here horizontal, and the red perpendicular in this plane that we have. Now, what we want to do now is actually look closely at one of these regions. So these orange regions, I just blow it up here on the right, and even look closer to regions 1, 2, 3, 4, and 5, which in the experiment itself, that's what Jairo was able to do, to actually, by restricting the aperture, could actually focus directly on these regions 1, 2, 3, 4, and 5, or whichever ones you choose, which are 1 micron size domains that seem to be monodomains, and to see if there's actually, in fact, monodomains, and be able from there to only observe the photoelectrons arising from these restricted regions instead of the entire larger region. Which you would do in the momentum ARPAS experiment. So turning now from the real space to the momentum space, you actually see here the results. The first one here on the right, on these 2 images here, you can see that the noise, the signal to noise ratio is worse because you have fewer photoelectrons arising. But in this case, you want to actually now measure this band structure that you're able to measure here to see how anisotropic it is, if the parity is violated or not. In order to do so, the best thing is to average over the different orientations in order to not look at the band structure itself, but the actual difference from its evenness, essentially, that you can actually now influence there. And plot this one, in this case, in a color plot. Here, the color blue or red is actually, sorry, there's somebody that is actually, okay, thank you for muting, is actually just how, whether it's, whether the difference from the even part of the spectrum, effectively. So here you're looking at the anisotropy. There's in blue and red indicates the anisotropy in the band structure, which now you can compare, now define this to this anisotropy, subtract the right to the left in this definition of what you call, antiferromagnetic paraviolation parameter, which then can be compared to the calculations that indicate a particular direction of the L vector. And in this case, indicates that the particular direction is up for the aperture here in position 1, and clearly seeing the parity violation. Not only that, if you now look at the other ones, in this case, you end up with particularly 2 and 3. They are opposite direction of the parity, indicating that they are pointing down. It also corresponds fairly well to this largest at around 0.4 electron volts, which is spectrum where you have the largest and is parity violation as a function of energy. And we also have a spectra that at low energy is almost, there's no, it's even actually, it's a function of energy that you have this parity violation. Also, if you look at 4 and 5, you have the parity violation being in opposite direction. In this case, that indicates that connected to the band structure calculations by Divers-Meckel, then you have opposite directions of the L vector. What this indicates also that here, for the first time, you have a direct microscopy of the nail vector domains, not just the orientation, not just simply knowing that it's laying flat on the plane or not, but that is actually pointing up or down. Once you, of course, determine this one to be up, it is arbitrary, the rest of them follow from that consideration. So this is also a similar novel tool in metallic antiferromagnets that has this parity broken to have this momentum microscopy. This physics is correlated or similar to what Phoebus had pioneered in electromagnetic materials and insulating ferromagnetic material, oxide materials, by using this double harmonic measurements. So the physics in here are correlated to that, similar to the second order magnetoresistance, and that has also been observed in these systems, but in a more indirect way. So with this, I wanted to mention maybe one before closing here, that there's other ways, of course, to image these slightly indirect domain vectors, vector domains of the Néel vector, and that is by, in this case, a little more intrusive, by coupling this to the permalloy. So having this permalloy layer on top of the antiferromagnet, this kind of manganese to gold. In the work where they show that here the as grown state and afterwards the permalloy that is on top, how the domains correspond to each other. So this is before it's grown, then you put the layer of permalloy on top and measure the domains of the permalloy, and they correspond 1 to 1. And then afterwards being able to measure the actual permalloy and then see the particular orientation that would correspond to the orientation given the correlation of the domains below. And that one, of course, is not a direct image. You're imaging the permalloy, but that is exchange coupled with the antiferromagnets. The permalloy is very soft and will follow the antiferromagnetic domains. But of course, it is kind of a two-step process in this particular case. And doesn't show, of course, the parity violation because it's not an ARPAS data. So with this, also mentioned that, of course, it is not just manganese to gold, but essentially we do have quite a lot of candidates. There's 22 from the 122 magnetic groups that allow for this direct type of PT antiferromagnets that can be chosen from and see them. Essentially 1/3 of the magnetic order materials, antiferromagnetic order materials, and here the caveat is that you do have to have fairly strong spin-over coupling to be able to see this breaking of the parity. And then the last one is this just a summary that we have here. We had the prediction of the antiferromagnetic parity in this PT antiferromagnets, in particular manganese to gold. And we've presented you the first observation, direct observation of this parity that can be also in connection, be used as a microscopy of the vector domains, of the Néel vector domains. So with that, I'll stop the presentation. And let's see, don't know why is it not stopping. Okay, interesting. And take any questions you may have.